I would like to welcome our first guest, Professor Bengt Gustafsson. Welcome.
Thank you and good morning. For me, Turku or Åbo is a bit special because I was here at an age of 16 for some weeks and moreover in love. So it was a chaotic period. And now the basic question for me today will be, do we move from cosmos to chaos or from chaos to cosmos? And I would like to start this with a democratic exercise, so let's vote for it. So, you know, since long, people have had the idea that we move from cosmos to chaos, from golden ages to whatever.
Define chaos first.
I won't. I won't. We'll come to a more accurate definitions later. But my idea is in the vote that you make the sense yourself to the words and you vote for any kind of scale. So if you want to discuss the universe or think of the universe, you can do that. If you want to think of your situation at work, you can do that. There will be a third alternative in this voting, and that is that the two things in a way balance or go back and forth or whatever. And I wish you not to be so Nordic that all of you vote for that compromise. Let's take 2 minutes when you discuss this topic with your neighbor and also look backwards on the row behind you to see if anybody has an opinion there, and then we'll have the vote. Please. So, please. It was even a little bit chaotic. So, how many are for the first alternative, that we or the world or the universe or society, whatever you think of, go from cosmos to chaos? Raise your hands, please. Okay. And how many vote for the route from chaos to cosmos? Okay, and then the mixed alternative, how many vote for that? That's a fair majority, but if you add the other two together, you get roughly the same amount. Okay. Now I will try to give some nuances to these words. And I start with a play by the Swedish playwright Lars Norén. I don't know if you have seen his plays. They are often very kind of, I wouldn't say depressive, but at least causes lots of agony for many people. He has a playwright called Romanians, and that concerns an immigrant couple in New York. It's an author who is struggling with his writing and an unemployed actress who prostitutes herself to support them both. They are visited by two young people, Mike and Myrtle, who live in the building's basement in a shabby quarter. They are members of a sect, these two youngsters. They are members of a sect called Children of Satan. And they are both drug addicts, however, supposed to be clean now. Myrtle, she plans to arrange everything in her life and also in other people's lives in shoe boxes and write the contents of the shoebox on the outside. Why this need to arrange or rearrange or sort? Why this need to order in boxes? Is it the human desire to organize the environment and thus lift ourselves out of chaos, to progress further into civilization? Or is it the need to label everything, to classify at any cost, to force everything you see into a scheme that you can master, so that you can control it, or at least not be overwhelmed by it? Organizing and classifying has always been important in the human world. There were certainly wise women and men tens of thousands of years ago who systematically collected minerals, plants, mushrooms, eggs, to test what they were worth as food or medicine, and for other important purposes like painting faces, curing leather, preserving corpses, mixing aphrodisiacs. Knowledge was collected and summarized in a classification scheme. Examples are easy to find. For instance, in the folk medicine in many cultures, alchemy, too, summarized knowledge on minerals and chemicals in a huge system. Whenever humans have pictured the world, sorting and classifying it has been important. Everything has been sorted, such as the elementary particles. Even heavenly bodies have different classes, early characterized by their supposed duties. A medieval image of the world depicts the earth at its center. It was surrounded by a sphere of water, the atmosphere, and a sphere of fire, everything in its proper place. And then came the spheres of the moon, Mercury, Venus, the sun, and Mars, followed by Jupiter and Saturn. And outside the spheres of the known planets came the sphere of the fixed stars. Then, in order, came the spheres of the ordinary angels, the archangels, the principalities, the virtues, the powers, the dominions, cherubim and seraphim, and on the top of it, God. He made it. But that was a different parallel medieval tradition, actually with an origin in antiquity. All life forms, from angels to man and other earthly creations, down to the lower creatures, were thought to be interconnected, like the links in a chain, the golden chain. Called catena naturae, the chain of nature. All things, no matter how small they were, are interlinked, wrote the theologian Nicolaus of Cusa in the 15th century. He said, among the species, such order is maintained that the highest creatures of one species coincide with the lowest creatures of the next up, so that the universe may be one, perfected, coherent. the chain is really unbroken, so that all intermediate forms exist somewhere, just not here. You may imagine a creature that is the combination of a giraffe and a fish. So there is then, most probably, a giraffe fish. Not here, for sure, but somewhere else. Because since God is almighty, it is almost blasphemous to suggest that he should not have created a giraffe fish. It was thought that these monstrous animals lived beyond the known continents of the world, and this is why such monsters were included in the outskirts of maps of the time. Next came the great expeditions to other continents in the middle of the second millennium, and many reports of the new animals and plants reached Europe. First, its imperial houses, trading companies, academies that had sent out the expeditions. And it became fashionable to have cabinets of curiosities of other worlds. Collections grew, and an effort was made to organize them, from dried alligator skins to coconuts, from rocks with strange inscriptions to the crania of man-like creatures. The objects were not only organized internally, one tried to find the connections between them and what we knew from the old world and the new world. The Uppsala professor Carl Linnaeus worked in this tradition, but he did not see himself so much an organizer as a tracker of the order in nature, an order established by God. The divine plan also provided knowledge about the nature of God himself. Linnaeus was, in a way, a natural theologian. It's possible that this, in a sense, enabled his great impact. He did not just adjust the system of nature to make a compromise with already existing human orders. If you wanted to trace the order of God, you had to be thorough and consistent, because the creation was by definition almost coherent, of course. In this sense, you had to be radical in this work. Though he classified life forms into all these species and families, he wished to see the unbroken chain in nature. Nature makes no leaps was one of his favorite thoughts. Linnaeus' classification scheme of life forms and other similar schemes, taxonomies, became the starting point for Darwin's theory of evolution. And similarly, one could use the classification of various minerals, earths and rocks, as a starting point for studying the geological development of the world. And later, the classification of different kinds of stars, each with its own spectral characteristics, came to serve as a starting point for the 20th century studies of the evolution of stars and galaxies. Let me take here one example and divert a bit by showing an attempt to present the late evolution of stars to a general audience. 2 decades ago, I was approached by a team from the Stockholm City Theatre who wished to set on stage a play on big science like particle physics and space physics. The aim with this play was not only to entertain or to present scientific facts in an entertaining way, but also to discuss such efforts in a societal context. Why should one construct this large hadron collider, the huge particle accelerator at CERN, or the European Very Large Telescope in Chile, to which, if I've calculated right, each of you who are taxpayers pay on the order of €1 a year? That is for the Very Large Telescope. For CERN, you pay more. Are those efforts really worth your money? And how should they be prioritized relative to other needs? Our theater collaboration led to a 50-minute play, The Secrets of the Universe, performed about 30 times with 4 actors, and also going for a tour through Sweden and a TV program. There was 1 musician and 1 scientist on stage, in addition to the players, and I was the scientist then. And I wanted to play one of the scenes from this play, and you will see appearing, except for me, in a younger version, Iva Boman, Helge Skog, and Lennart Svensson. So, please.
Här måste vi pröva. Absolut. Här måste vi pröva. Bra, det är klart. Har ni ryggsäck, matsäck, termos, apelsin? Då går vi! Så var vi av med dem då.
Frågan om universum är sammankrökt på det här sättet eller inte, den hänger ihop med hur mycket materia det finns där. Om man ser hur galaxerna rör sig i förhållande till varandra, så verkar det som om det finns ganska mycket materia som vi inte kan se. Tyngdkraftverkningar på galaxerna. Det kan vara så att den allra största delen av universums massa är sån här mörk materia som vi inte vet vad det är. Om det är svarta hål, om det är små, svagt lysande stjärnor, eller ännu mer sannolikt att det skulle vara partiklar som inte växelverkar gärna med annan materia, som bara märks genom sin tyngdkraft. Och det är bland annat sådana partiklar som vi vill försöka kunna fånga, som de här små ljusglimtarna i eran sjö. Nu hör jag att de har kommit runt. Antingen så har universum mycket mer sammankrökt än vad jag trodde, eller också så har de fuskat. Men i varje fall, plats nu för 3 stjärnor!
Varenda stjärna för en hopplös kamp mot tyngdkraften som slutligt drar den samman.
Den enda motkraften är gasens tryck. Det räcker bra så länge vi hålls varma av heta kärnprocesser i vårt inre.
Till slut tar ändå denna värme slut. Då krossas vi under vår egen tyngd.
För lätta stjärnor, så som jag och solen, lär det ta många år, miljarder dit. Sen kramar tyngden samman mig till dvärg. Och jag blir hopträngd till en klump som jorden, fast ännu tung som solen.
Och en tesked av himlakroppen rymmer mycket mer material än vad en bil består av.
Jag är en lika tyngre stjärna jag, som blåvit bösar i Orions bälte. Mot slutet av mitt liv blir tyngdens bänkpress mig övermäktig, så att minsta småatom knäcks som en hasselnöt och sammanklämd till något inte större än ett berg blir jag. En stjärna av neutroner!
Här väger varje tesked himlakropp mer än den samlade materian i alla Sveriges bilar, bussar, tåg och tyngdkraften blir rent katastrofal för den som tänker sig att gå på ytan.
Går den att gå på? Har den stadig skorpa?
Ja, visst. Och här finns berg, blott centimeter höga.
Det var då inte mycket att bestiga.
Försök du. Mycket mera energi lär du behöva än du måste ha för att kunna bestiga Kebnekaise.
Vi kan väl göra ett försök ändå.
Reakta dig. Ty innan du har hunnit att ta ditt centimeterhöga kliv lär du av tyngdkraften ha plattats ut till en tunn hinna över himlakroppen.
En blöt fläck blir du bara, pysen.
De allra största stjärnorna, som jag, får ännu värre trubbel med vår tyngd. Den drar oss samman till oändlig täthet. När energin tömts ut i vårat inre, så blir vi bara svarta hål till slut.
I de svarta hålen
I'm open to questions or comments on this. Does this work? Please.
What was the purpose of that play?
The basic, the basic purpose, as I indicated, was to try to discuss the efforts in big science, like in this case astronomy and space science, and the cost for it. The framework of the play is the following. We then planned to build a big neutrino detector, 100 by 100 by 100 meters, in the lake of Torneträsk in northern Sweden. That's a very beautiful lake, and there is a local people who live from fishing in it. And our plan was to really use 100 by 100 by 100 meters of water with detector in the lake. It would destroy some of the fishing, it would affect the landscape. Question was it worth it? And that is the framework of the play. So basically I, as the initiator of the project, went to the local village and with 3 assistants playing and explaining interesting problems in my science. And then the local people reacted on it. It worked very well in Stockholm, and then we went up there and gave it in Kiruna and got 2 hours of discussion afterwards, and a very intensive discussion. Later on, we moved the whole project because Torneträsk isn't clean enough. You need very clean water because you need to see faint light signals at great distances. We moved it down into the Antarctic ice to a depth of 1 kilometer down in the ice, the so-called Ice Cube project, which is now running and collecting data. I asked the question, did it work? And what's the cost for doing this except for the pleasures and the money? I mean, what's the cost in presenting science in this way? You think it's fine, or? Nobody is critical?
You have to simplify it, don't you?
Yes, and in which way? I mean, there's a fundamental thing we do, and you see it very clearly here. You personalize. These stars are living. And of course, that's a kind of cost, perhaps. Yeah. Question is it?
I mean, you could present it in a non-personal way as well. Art doesn't have to be personalized.
Yes.
So it's not, but in this format, yeah, certainly.
I think personally that this is a striking method. It's a very, very kind of moving method, and I'll come back to that later in my presentation.
Yeah, I mean, that's a great advantage.
Yeah. I
mean, it's always a trade-off.
Yeah, it's a trade-off. But I think very much of natural sciences involve a personalization.
Yeah. I mean,
we pretend that these things are like us.
if you just present slides with spectra and try to explain what you're doing scientifically, and you won't reach anybody. So
no, exactly. Okay, I'll come back to this issue. Now, back to ordering. I mean, this is also a kind of ordering when we discuss stars of different types. But if you order animals or stars or a collection of photographs of unknown relatives, as I've done recently, if you order these in different groups according to appearance, it's tempting to speculate not only on their interrelationships, but also on their order in time. And also, not only order in time, but order in society. It's tempting to arrange your ancestors in order also of status and priority, at least if you have full body pictures so you see their outfits. And this term, order of priority, reveals how we think. We imagine plants and animals in a long parade, as if they were crossing the gangplank of Noah's Ark. But this one-dimensional linear order is in fact unnatural. It is characteristic of our one-track way of thinking and organizing, but not of nature's way of working. In reality, a lot of different things happen at the same time. All natural development branches out, goes through twists and turns, back and forth, splitting off in different directions. Yes, this natural order may look chaotic. Constant and erratic changes of circumstances occur, often small ones, such as mutations of the genetic makeup of individual organisms, sometimes more drastic ones, such as floods or ice ages, sometimes even cataclysmic ones, such as collisions between planet Earth and other celestial bodies. Such catastrophic events, they occur randomly. They destroy, but also open up new avenues for new directions of evolution, new possibilities for small, until now unnoticeable twigs on the complex tree of evolution. What carries life through all these changes is the variation among life forms. Due to variation, certain individuals and species happen to be equipped to handle new circumstances better than others. They can produce more numerous offspring, and as a result of this, a pattern of life forms, with species and families appearing, and we discern and name them like Linnaeus did. But the pattern is really our view of nature's structures. The pattern is our view of nature's structures. And we must indeed ask ourselves how much of the pattern of nature that is due to us, reflecting our own way of thinking. Certainly, many of our classifications are exaggerated and superficial, since humans are good at discerning differences more than similarities. This ability seems to be part of our own nature. Perhaps it has some value for our survival, as when we note the differences between the delicious mushrooms and the poisonous white toadstool, that is, vitflugsvamp. We take care to divide the world into classes such as edible and poisonous, good and evil, us and them, female and male, minor and major, body and soul, normal and strange. In some cases, at least academic ones, we may discern a few other classes, such as pass with distinction, pass with merits, pass and fail. But reality is often more complex, with more dimensions, but also with more borderline cases rather than typical ones. Sometimes scientists remind me of children who may be experts in classifying cars on the basis of small details, arrangements of lamps, a small bar in the grille, the way the rear view mirrors are attached to the doors, while the cars are often built on the same chassis and constructed using the same software, a fact that the young classification nerds are not aware of or interested in. In the same way, the rich variety of shapes in nature might well overshadow the underlying very few and even simple principles. In this ordering of nature that we are engaged in, a special and important activity is the discovery or constructions of laws of nature. Long ago, these laws really had a legal authority. For instance, in 1474, a rooster, that is a cock, is reported to have been put on trial in Basel for the heinous and unnatural crime of laying an egg, which the honorable citizens were concerned was spawned by Satan. And the egg most probably contained a cockatrice. You see a cockatrice here. They are dangerous. Thank you. The bird was sentenced in a solemn judicial proceeding to be burnt to death alive. Laws of nature should be adhered to. Breaking them was a provocation against the inventor or upholder of the laws, a provocation against God. In physics, we are, at least since Galileo's time, engaged in tracing, discovering, or constructing mathematical laws of nature. The book of nature, as Galileo said, is written in a language of mathematics. You know, there were two books. There were the scriptures and the book of nature, in which God revealed himself. And the book of nature, Galileo claimed, was written in mathematics. He was right in this, and we don't know why. Why does mathematics work so well? Not only in describing the results of our measurements in a consistent and efficient and beautiful framework, sometimes, like in quantum mechanics, with accuracies to the 12th decimal place when we control with measurements. It's also a framework which is so powerful, mathematics, that predictions of qualitatively new phenomena may be made with it. We did predict new planets. We predicted antiparticles. We predicted black holes. We predicted the Higgs boson, etc., on the basis of mathematical principles. And please observe this, even if the mathematics we have built to fit the local nature, even if that's done that way, we are able to predict very absurd phenomena which we would never think of if mathematics didn't tell us, like the properties of black holes. How comes that these things were so efficiently predicted? Why? Why this unreasonable effectiveness of mathematics in the natural sciences? To cite the title of an essay by the famous theorist Eugene Wigner. Is it because nature is constructed this way, a kind of artifact? That is a pious explanation. which echoes through the history of physics, even up to the atheistic Stephen Hawking, who characterized the hypothetic goal, the theory of everything, as it was called. He characterized that as knowing the mind of God. Is this unreasonable effectiveness instead present because we carry the patterns of nature ourselves, also of nature in its most distant and unfamiliar manifestations? Within us, like some archetypes, as the 17th century astronomer Johannes Kepler and the 20th century physicist Wolfgang Pauli conjectured. Are these patterns of nature, the mathematical patterns, inscribed into us from the very beginning, and why? Or does mathematics work so well because we are highly selective? Pick out what we can describe with what we happen to have at hand at the time of discovery and forget the rest of it. All this other chaos around us. To cite Isaac Newton, I was like a boy playing on the seashore and diverting myself now and then, finding a smoother pebble or a prettier shell than ordinary, whilst the rest of the ocean led in front of me unknown. Or is the reason for this mathematics working so well because our experience of the surrounding world is much more our construct than we, as natural scientists, are willing to admit? Is the world like our way of thinking because we actually construct it that way? To cite Arthur Eddington, a leading astrophysicist from last century, we have found a strange footprint on the shores of the unknown. We have devised profound theories, one after another, to account for its origins. At last, we have succeeded in reconstructing the creature that made the footprint. And lo, it's our own. We do not know what the reason is for the success of mathematics in science, and on the possible deeper level for our connection to nature or projection onto nature of our way of thinking. So, as a theoretical astrophysicist, I would like to pose this question when we work successfully so, at least sometimes or even often, with mathematics in describing nature. Is this really reflecting nature in a deep way? Is it showing that nature is in order? Or is it my wish to have order in it, which I project out into chaos? I think this is a place where you may contemplate a bit. So I suggest we have another 5 minutes of discussion in between you, and then you can give your views on these issues. If you can solve the problems for me, I would be very happy, but I'm willing to defend my own ideas too. So please, 5 minutes discussions.
Kun aurinko paistaa, niin suokorvan
So, I enjoy the fact I have to wait for you. It means that discussions are intensive. So, who wants to say something? Yes, please.
The question why is not a scientific question, it's a philosophical question. The problem is that this common audience may think that your question is scientific, but it's not. The second point is that mathematics is not a science, it's a technology, it's a tool. Any tool can be used for empirical research, of course.
On the second remark, I fully agree, even if, as you know, some people have different opinions on that. But I agree with you. I think it's totally man-made. It's a tool. But it's quite interesting then that this tool can be used for unexpected things, very unexpected, in fact. You know, to take one kind of drastic example, what you do when you, say, predict the existence of black holes with all kind of absurdities they show, to me, it's a bit similar to if you would try to describe the nearby hills by some kind of polynomial which you fit to them. You know, you can make a mathematical description of these things, and then you use those to predict the mountains on, say, the Saturn moon Titan, and you calculate those mountains and you go and look and they fit very nicely. This kind of thing is what mathematics does. Sometimes, not always, but sometimes, and that's astonishing enough to me. The first point you made, I didn't understand that. Do you want to repeat it?
You can't use philosophy and science.
But I have a question.
Okay, please.
I'd say that this scientist, Bengt, is a good scientist because he's a philosopher as well. And Henrika and I, we were discussing his point of us being unable to see reality for itself. We always look at reality, cosmos or chaos, the universe, everything there is, through our own eyes, with our own thinking in the background. That's philosophy. Knowing that or remembering that, I can't help but thinking that all that happens is the use of energy. So energy has an origin. But then again, as with stars, the complicity will, at one point, some point, stop. And all will be reversed when all energy is used. And perhaps everything will become one homogeneous soup, which is, to me, order, cosmos. Thank you.
I think those perspectives will appear in my presentation afterwards. I won't comment on them now, but I'll come back to them. More? Yes, please.
Before the scientists found the Higgs particle, we had 4 forces. And now I guess we have 3 forces: the gravitation, electromagnetic, and the atomic force, simplified. Is it feasible that we eventually will find some other force, like a spiritual force? And what kind of proof would the scientists need to accept this?
First, is it feasible that we find other forces of nature than the ones we know? at the moment, and I think it is, yes. There's nothing forbidding that. Of course, we don't want to have more than needed. We follow what's called the Occam razor recipe to not complicate if we don't have to. But it's feasible if there is such an extra force. The problem may well be that could be a very long-range force, for instance, or an extremely short-range force. If it's very long-range, we'll have to look over perhaps greater distances than we can ever do in the universe to see the effects of it. Or if it's a very short range, we may need much more higher energies than we have at hand, even with the LHC. But we don't know. And maybe LHC will point out needs for additional ingredients of this sort. You asked what will have us be forced to admit it. I mean, what will force physicists to say there is another force? And I think, as usual, experiments are key things here. And if you can't fit phenomena into the current scheme, and if you can't modify the current scheme with the known forces to take care of observed phenomena, then you had better do something of that sort. Time for one more. There's two more then. You and you. Yes, please.
You mentioned three alternatives, that the book of nature is totally written in mathematics, or that we are selective and we see the regular parts of nature, or that we are constructive and that we create order in nature. But are these different alternatives really? For instance, chaos mathematics has discovered patterns in what seem to be chaos. Yeah. You have Lorentz attractors. You never get, in a moving system, you never get back to exactly the same point, but you move in a pattern that is regular and takes the same turns every turn that
if you continue like this, you will give my talk.
Oh, okay.
This is what I'm going to comment on later. Yes, please.
So these three alternatives are really the same. We call some patterns in nature regular cosmos and some chaotic. And in doing that, we mirror the regular parts in ourselves. And we continue mirroring more and more parts as science proceeds.
Yes, yes. I should say, just add to that, I have a son who is philosophically minded, and he brought up the following issue that you, Bengt, or Father, you predict that and this property of galactic clusters and whatever. But if I take my wallet and go out on my balcony and start dropping my bills, I cannot calculate, and you cannot calculate, where on the grass it'll fall. So that's an example of something we have, as physicists, just refrained from discussing, even though bills may be important for us. Okay. You had also a question, yes?
Yes. Your question made me remember from the early 70s when I learned about this Heisenberg principle, which, if I recall it rightly, the observer will influence the thing she is observing. And this you can see in both in quantum physics and is very observable in social sciences.
Yes.
So, but I guess that's a bit what you were getting into, and you will be getting into both and. Yep.
Yes, I think that is, of course, a fundamental fact, that we are interacting with everything we observe, even though we don't interact so much with the stars. But still, you are right in pointing this out, that this distinction between the observer and the object is fuzzy and sometimes just not relevant even.
Okay.
Thank you for your comments. Until now, I have discussed order in nature, how we discover it, establish it, describe it, uphold it. And now I shall turn to the other side, chaos. Since very long, yes, the early days of the Greek philosophy, and even of Judaic cosmogony, use of the most common ideas about the world has been the following. It starts in a chaotic situation, and then ordering principles set in more or less gradually. Cosmos forms out of chaos. And since several centuries, this has also been a generic idea in scientific physical cosmology. The reason for this, except for tradition, is both principle and practical. We try to construct scientific theories following the old medieval recipe called Occam's razor. Here understood as you should not make unnecessary assumptions or build your theory on as few hypotheses as possible. And it is a fact that chaos may be specified with quite a small number of numbers compared to an ordered situation. A well-ordered system carries a lot of information and needs a lot of information if you wish to tell somebody else how it's organized. While many chaotic situations can be easily characterized by a few principles and a few numbers, parameters, typically less than 5 numbers. Give me 5 numbers and I can describe chaos. This is not only a principal advantage, but also a practical virtue. You can think of starting a computer simulation on the evolution of the universe from chaos to cosmos with just loading a few parameters and laws into your supercomputer. And then just wait. But I bet you will be disappointed. Hardly any universe will result from such an exercise, at least not any habitable one. Instead, almost all your universes will end up as fiascos. After huge waste of taxpayers' money for your computer usage, you will have to admit it didn't work. My model universes did not work. No cosmos came out of this chaos. Why not? There are several reasons, at least 3. The first one is called the second law of thermodynamics, which I think was mentioned before, not explicitly, but indirectly. That's also called the entropy law. This basic physical principle states that any physical system isolated from the surroundings, which is let to evolve, will increase its entropy, that is, increase its disorder. Order will gradually be vanishing. Thus, it will go from a more ordered system to a less ordered system. It will become more chaotic as time goes, not the other way. Now, it's not trivial that this law may be applied to an infinite universe. Is that isolated as the formulation of the entropy law required? Anyhow, the law seems to suggest that nature shall certainly have difficulties in making the program from chaos to cosmos work. That was the first problem. The second problem that amplifies the difficulties I mentioned. The universe is rapidly expanding. dispersed by the winds of the heavens, to cite a Swedish saying, skingrad för himmelens vindar. The universe did really evolve rapidly in the earlymost phases, and still it expands in all directions and everywhere, such that it is indeed hard to collect parts of it to any complex structure at all. As my wife, who is a school teacher, said, it's roughly similar to collecting the pupils the 2 days before the exam to do anything meaningful. The major force that can now collect matter, or could do it, and form structure is gravity, but that is not at all strong enough to get matter together in most places, even if it is amplified by considerable amounts of heavy, dark matter. The argument from the skeptic concerning the validity of these two objections may be that the second law of thermodynamics and the strength of gravity may not be given once and for all. Let's assume that these circumstances are changed, such that the second law gets weaker and gravity gets stronger. However, such experiments and other similar ones, thought experiments I should say, when the laws of nature are artificially changed, show that it gets much worse. Indeed, the laws of nature of our universe are practically optimal for galaxies, stars, atoms, planets, life to form and survive. I'm not saying it's simple. If I saw, being the natural scientist I am, if I saw the universe after 1 second, this 1 billion degrees hot gas, dense as water roughly, rapidly expanding, consisting of hydrogen and making some helium, lots of photons, that is light, and electrons and neutrinos. If I saw that mess, and somebody asked me, can you do any galaxies here? Can you do any stars here? Can you do any planets here? Can you do any atoms here? Can you do any humans here? I would say not a chance to do it, even though I think I would know the result. It's very difficult to get it working, even with the laws of nature we have. But the point I make now is that if you make thought experiments and change them, even change the constants of nature in the second or third digit, it gets much worse. Now, to prove this is difficult. It's difficult enough to understand, as I hinted at, how we can get anything out of the universe we know. How could we discuss universes we don't know and don't see? But in principle, a number of these arguments are quite compelling. I worked on one of these in detail, and that's the strong force which holds together the atomic nuclei. If you increase the strong force by a few percent, you will make helium, not very much hydrogen in the beginning, and helium is not so constructive, not so easy to use for chemistry. But okay, you get some hydrogen, but then you will burn your hydrogen to helium to carbon to oxygen and get hardly any carbon. And carbon we do need to make any kind of life. If you decrease your strong force in the second digit, a few percent only, you don't get any carbon at all. You don't proceed the way by burning nuclei in the centers of stars any important way beyond helium. So, to get carbon, you need the strong force we have, and rather precisely that strong force. Not stronger, not weaker. Okay, so such experiments leads to a third argument against the chaos to cosmos cosmology. We would need to have very special laws of nature in order to get any meaningful structure in the universe. And these laws happen to be the ones we have. So there wasn't a chaos in the beginning, if you by chaos mean something which was entirely different in terms of laws of nature from what we actually see. How could we be so happy to have been born in such an ideal universe? Well, where else would we be born? So, we may draw the conclusion that it's no trivial business for our universe to form us, but that it would certainly have been much more difficult if it had happened to be different from what it is. So the laws of nature and the starting conditions of our world are very special. They cannot at all be characterized as chaotic. We start in order. I mean, I wish as a scientist it had been different. We had, for a long time, had this dream that we could understand it from practically any principles, any starting conditions, and we get it all. But we are very far from that dream. There's one way out of this dilemma, though, if you do not wish to ascribe to intelligent design of arguments, of course, which I, by the way, would regard as scientific capitulation. That way, the scientific way out here, I think, is to say that we have had and have an enormous amount of different universes, and most of them just without any potential to form galaxies or stars or atoms or planets or life. If this chaos of worlds then is big enough, numerous enough, and we talk here about billions of billions of billions of billions of different universes then, there happens, of course, then to be one where we could be formed. And that is where we, fortunately enough, are. Where else would we be? So, in this way, you could save the idea of an evolution from chaos to cosmos. Not for our special universe, because that happened to be well ordered, but for the full ensemble of worlds as a collective, you could talk about a chaotic start. The cost for this multiverse hypothesis is, however, as huge as the size of the full ensemble of universes. You have to conjecture an enormous world of unsuccessful universes, all impossible to observe as far as we know, just in order to explain one of them. So much in vain, as one of my colleagues said. And as with an intelligent design hypothesis, I think also here you give up a considerable part of the level of ambition of scientific explanation. The understanding of why our world is as it is risks to become just an endless just so stories ending with else we would not exist. You have read Rudyard Kipling's Just So stories. Why does the elephant have such a long nose? Well, it went as a child, or as a baby, it went to the Nile and drank water with its normal mouth, but there was a crocodile and pulled it out. That's a typical Just So story. And here we have similar things then. Why, for instance, is the charge of the electron as it is? Well, if it wasn't there, and then a long story ending with, and planets cannot form, and so I cannot be here. You see? I don't think, as a scientist, I'm not so happy with those kind of explanations. I would like to have more general explanations which are less dependent on our own existence. But sometimes you don't get what you wish. Even scientists don't. And not only when we don't get money. After having contemplated these different perspectives of the laws of nature, I decided that they are so complex, with ideas deeply rooted in us and partially in subconscious layers, that a more profound attempt to deal with them should be attempted. And I was then guided by the small experience I had in setting up the play, The Secrets of Universe, of which we just saw a part. As you have seen in the play, we illustrated how stars finish or die, if you wish to personalize them. In order to show the alternatives that are at hand here, 3 actors, as you saw, represented 1 star each by reading monologues in blank verse in a Barockian or Shakespearean style, dressed up in antique costumes. I wrote those verses, constructed them at my table and looking back at some Shakespeare to get it roughly right and all this. And then I sat on the front row, and these actors made it. They had rehearsed it independently of me, and I was deeply shocked because I was moved. I mean, of course you say, that was ridiculous, just like a kind of very simple student set up a comedy of some kind. Yes, it was very simple. It was not art of a high level, except for, I think the players are very good. But I was deeply moved. Why was I? I think these scenes displaying the agony of dying stars change deeper roots in my own mind and deeper experiences. I worked all my life with stellar physics. I've never been so moved by it. And there was a lasting impact on me, I believe, by raising my awareness of the fundamentally dramatic and even tragic sides of stellar evolution. I study stars who die. They have planetary systems around them. Who are living there? So, guided by this experience, I looked for an opportunity to confront the complex questions concerning the laws of nature in an artistic form. In Stig Dagermans last work, the unfinished fragment of a novel, 1,000 Years with God. In this fragment from the 50s, God visits the house in London where Isaac Newton is about to die. It begins like this. I'll read a translation by Stephen Hartman. There are times when God tires of his usual guise of light and silence. Eternity sickens him, and his cloak, kappa, falls. A shadow takes shape among the stars, and the night moves in. In the house of Newton in London, preparations are unwittingly being made for his singular visit. The evening is late, and through the rain, a carriage glides along the street towards Newton's house. It passes through the arched gate and circles to its stop outside the house as oak leaves drift incessantly to the ground. 1,000 Years with God tells how God visits Isaac Newton on the day of Newton's death. In his room, Newton has a collection of silence that he has gathered from all parts of the world, and it's understood that nobody is to speak in Newton's presence. To be sure, he has a mute butler whose heart beats without a sound. He is the son of silence, and Newton loves him. But with God's presence in the room, the silence suddenly is broken. God dispels the silence, and the mute butler speaks. Then God proceeds to abolish the law of gravity, Newton's holy discovery. As the butler drops a tray carrying Newton's afternoon tea, the tray quietly floats up towards the ceiling, where it hovers. When the butler makes a move to bring it down, he also rises and hits his head against the ceiling. Later, at Newton's funeral, embarrassed relatives and dignitaries use heavy chains to keep the coffin from taking off into the air. It's a mystic and provoking story of great power, well worth reading. It's a theme book. You find it in your library. Margareta Åsberg, a leading Swedish choreographer, modernist. Peter Gärdenfors, who is a professor of cognition research in Lund, and I discussed during several years whether one could make a performance based on this story. Finally, Margareta got money for staging it at the Royal Swedish Dramatic Theatre in Stockholm. With Margareta at the lead, it was made to a full evening event some years ago, with actors, dancers, a choir, projections, sculptors, and 2 scientists, Peter and I, on stage, or I'll come back to on stage. Both the music and the pieces of art, there were 3 composers who made original music. There were a number of pieces of art at display in the performance. And also these composers took part in the very work, and so did the actors behind the performance. It was performed 36 times with full audiences sitting on galleries above projection screens along the side of the stage. The stage itself was covered with sand and gravel. One basic reason why I engaged in this project was the possibility to discuss in artistic form the question, what are the laws of nature? That question is discussed by Dagerman. God breaks his own laws. Newton gets upset and argues that this is against everyone's interest. The believers, because the believers in God, they will believe too much from God. And the non-believers will be very frustrated. No, we need law and order. We need my law of gravity. You had better follow that. In the end, they make a deal, it seems. Newton agrees to breaking the law. As a dead body, he doesn't follow it. And God is allowed to become a human, which he always wished. Okay. A question then is, why should one use an artistic form to discuss these difficult matters with the laws of nature? Why don't we keep the discussion within the scientific seminar room? And before answering or discussing that important question, I want you to help in doing that. I would like to show the beginning of this play. I have to now warn you, because we speak Swedish. It's performed in Swedish, and I don't have any subtitles, unfortunately. There's a lot of music and dancing in the first part, but there's a boring presentation by me and by Peter. I will return, if you can turn down the sound then a bit, I'll roughly say what we do. Okay, so please run it. I will run it from the beginning. I have to get it in order, though.
Ibland tröttnar Gud på sin gestalt av ljus och tystnad. Evigheten väljer honom. Hans kappa faller. Vi ser en skugga ta form bland stjärnorna. Natten kommer. I Newtons hus i London bereder man sig ovetande på det sällsamma besöket. Sent på kvällen kommer en vagn glidande i regnet längs gatan där Newton bor. Kör in genom portvalvet till Newtons hus, gör en sväng runt den mörka gården. Ekarnas löv faller oupphörligt. Newtons betjänt reser sig från trappan och vacklar ut i regnet, midnatt och drucken.
So this is part of it. It's altogether about 2 hours. And you saw some of the ingredients. You saw Anja Birnbaum dancing. She comes back several times. And you saw the choir descending from the ceiling in balloons. Members of the radiokören. Thomas Jennefors's music. And you saw one of the actors. What you didn't see, I promise you, but we don't have to see it, that's the scientists. We have, in this play, we have 4 dialogues. We interrupt, and these dialogues are improvised partially, while the rest of the thing is very kind of patterned from the beginning. But we improvise. We have dialogues, and the idea of Margreta was that we should stand among the actors and take part in the play, improvising, and then start talking, and the actors should go to frozen positions and then continue. And here came the real crisis of the performance. We spent lots of time in rehearsing this, and the actors made an upheaval. They couldn't accept having scientists on stage. Because we don't have the proper training, you know, we move like, yeah, do lots of things we shouldn't do on stage. So in the end, the situation got into the leadership of the dramatic theatre, and the tradition is then, if there's such a conflict between the director and the crew, the director himself of the theatre has to take over. So he entered and said, I command from now on, you guys, you stand on the galleries. So here was the stage, and there were 2 galleries like this, and the audience was sitting along the galleries above these projection screens, which you could say. And we were then standing and having our dialogue across the floor, across the scene where the actors were standing in frozen position. They got us away from standing down with them. And that was interesting. In fact, I think it showed in a very kind of simple way the problems of integrating arts and science. The scientific discourse in the best of worlds has to be quite free. And of course, theatre is sometimes very free, but if you want to have a crew of choirs, musicians, artists taking part, they have to know exactly what will happen. At least it's difficult for them to improvise. Anyhow, we made the performance, and it was considerably discussed. The theatre and the opera reviewers were positive, some quite enthusiastic. They regarded it as a new thing, and I think it was a new thing. But they were also quite perplexed. Some people thought that these scientists shouldn't be there. I mean, why these kind of discussions with the academic tradition in the middle of such a beautiful performance. And other people said, this is the point. The discussions were the best thing. Physicists and other people who knew what we talked about in detail, they were quite happy with our performance, but they didn't like the dancers and all this flummy stuff, you know. I think we succeeded in discussing the laws of nature because a play is about that. It's really provoking when Newton, you know, in the funeral scene, he really lies at this height, and the chains are lying around him, seem to keep him to a handable level. Of course, in practice, some chains were stiffened, keeping him up like that. Thank you. Okay, we can do it like that. Thank you. I think the interplay between our cosmological instincts or archetypes on one hand, which we aren't fully aware of, and the real nature on the other hand, came to focus in my interest as a result of this performance. So I don't know what people learned from it, probably lots of different things, but I learned that this is a subconscious background which I have to consider if I do cosmology seriously. In the last part of this talk now, I would like to argue for a chaos as such. And I need another one. There we were, good. Because chaos is, even if it's not a starting point, it is as an ending point more generative concerning order than we have understood before. Already half a millennium ago, 500 years ago, Leonardo da Vinci was fascinated by whirlpools in water streams, seeing small worlds within large and even smaller worlds in the small ones and bigger ones composed by the large ones. His drawings of these patterns are reminiscent of the ones he made of intricate women's coiffures. The pattern of also non-living nature are truly fascinating and intricate. Think of the worlds of galaxies, for instance, or the crystal patterns of snowflakes, or the cloudscapes of our atmosphere. Patterns show up in systems composed of many parts, such as starscape of galaxies, myriads of atoms in snowflakes, clouds of gas molecules in the atmosphere. These patterns are very odd. They sort of arrange themselves. They emerge without the influence of a forceful outside agency. How does this work, this self-organization in patterns? In the early 19th century, everything seemed to be so good in order. The planets encircled the sun, and true enough, they perturbed the orbits of each other. But Newton, in fact, he worried about this. He felt that the planetary system might, in the long run, be unstable as a result of these perturbations and collapse or fall apart. In such a case, Newton proposed that the otherwise relatively inactive God could intervene. But Laplace, the radical French, studied this further and found that the perturbations to the first approximation would only generate small periodic effects in the orbital elements of the planets. That is why he responded to Napoleon's question on where God, or why God did not appear in his thick book of celestial mechanics. Laplace answered, "I do not have any need for that hypothesis." He didn't. The planetary system was stable and could continue like a large clock forever, he thought. But this was only in the first approximation, though. The final proof was not given, and that is why King Oscar II, Oscar II of Sweden, decided to celebrate his 60th birthday in 1889 by a competition. The winner should contribute to resolving this issue of whether our planetary system was stable or not. Good to know. The winning contribution was that of a young French, already famous mathematician, Henri Poincaré. His essay was on a simplified situation, the case with three bodies interacting gravitationally. It contained a curious discovery of great importance. Some orbits could become extremely sensitive to the initial starting conditions. Here are some examples from his work, where you see how the three bodies interact and find all sorts of orbits, some of them ejecting, like the upper one, upper right corner, one of the bodies from the system. And he found that a microscopic difference in the speed of one body might in some circumstances lead to entirely different orbits, even a breakdown of the whole system. Poincaré had found that very small changes in the system could eventually lead to entirely different behaviors. And this was the discovery of chaos, a fundamental discovery, but it took more than half a century for its importance to be fully known. One was used to the idea that small changes in nature would only have small consequences through expressions like, although expressions like, for want of a nail, the battle was lost. Liten tuva välter ofta stort lass in Swedish. Such expressions were common in many languages as proverbs. In the early 1960s, a young astronomer at l'Observatoire de Nice was busy in calculating orbits, not for planets in the solar system, but for stars in clusters and galaxies where all stars moved under the influence of gravity. His name was Michel Hénon. He too was fascinated by the question whether star systems really were stable or whether they might disperse or collapse. The problem was known to be almost insolvable, but two things made it easier. Computers had now been developed and reached a level of sophistication which was enough for his problem, even if they couldn't be compared with your laptop at home today, of course. Moreover, Hénon realized that he could simplify his equations by erasing some terms and still retain enough of the characteristics of the situation to grasp the nature of the problem. It appeared that the orbits usually looked normal, but if the starting speed of a star was increased, its orbit could become erratic and sometimes completely chaotic. And Hénon found nevertheless some remarkable regular patterns in the way orbits progressed towards chaos. That was a very important discovery. There seemed to be unexpected new regular patterns, new orders in the way towards chaos. At the same time as Hénon, Edward Lorenz was working on weather forecasting in Massachusetts Institute of Technology on the east coast of the US. Lorenz had programmed his computer to solve equations that modeled weather systems, areas of high and low pressure. In his model, temperatures rose and sank, half regularly and often periodically, but sometimes abruptly, as weather systems passed over the computer screens of his. In the future, when more powerful computers would be there, it was thought the weather could be forecasted in detail years ahead. But Lorenz discovered that very small changes, for instance in pressure, could lead to drastic alterations in the virtual weather development. He argued that a seagull flipping its wings could change the weather. Later he put it in a more drastic form. Could a butterfly flipping its wings in Brazil cause a tornado in Texas? The phenomenon thus came to be known as the butterfly effect. It seemed to render long-term prognosis impossible. Minute rounding off errors in the calculations would grow enormously and prevent all certain predictions for long term. And in practice, one had to feed in enormously detailed starting conditions in each model run, like pressure fluctuations due to seagulls or butterflies. There was certainly no hope in doing that. This butterfly effect has not escaped criticism. Many times small changes may grow, but their effects may even out and never reach the grand scale. It might never be a tornado, just a faint breeze among the flowers of the Amazons. But which systems that are sensitive to the effect and which are not is not yet clear. Like Lorentz decided to simplify his equations further to be able to study them closer. He left out some details and now had a sort of toy model that his computer could easily handle. He found that the irregularities, the unpredictable wild cards, could, in spite of their capricious character, be handled and described by an endless curve that never intersected itself and constantly formed new loops. The curve he found came to be known as the Lorentz attractor, which was mentioned in the discussion earlier. And so emerged chaos theory. Regularities in chaotic systems were tracked. Regularities appeared not only for each and every system in nature that displayed chaotic processes within themselves, but also when different systems were intercompared. There were thus similarities between the way bad weather cyclones proceeded towards chaos and how whirlpools in streams and stars in galaxies or Jupiter's famous red spot, etc., became chaotic. The dynamic processes showed deeper similarities than the mere appearance of the phenomena hinted at. It seems today that many, perhaps most, of nature's systems develop through entirely or partially chaotic conditions, and that these may be important in building the complexity we see around us, in dead matter, and partially also in living matter, I suppose. We have begun to understand that patterns in the systems of nature never can form when the systems are in equilibrium, but when they are pushed towards chaos, towards positions where no predictions can be made and the order is fully at risk. On the way towards this total disorganization, and sometimes even as a result of that, even more complex structure emerges, often shaped in complex but still basically simple ways. And finally, the system is pressed across the line and becomes fully chaotic, and structure vanishes. These structures are often self-similar on all scales, a fractal structure. As the 19th century Swedish romantic poet Erik Johan Stagnelius put it, chaos is the neighbor of God. Yes, I do not wish to make this idyllic. Complex Yes, beautiful structures also form according to similar principles as those discussed here in the mushroom cloud of a hydrogen bomb. I cited initially the playwright Lars Norén. He, in fact, has also written a play directly citing Stagnelius. The play is called Chaos is the Neighbor of God. In a related poem he writes, listen now, "It is nearly absurd to believe it, a butterfly in December, a small light in the great light, as a little unimportant pain only in the really great pain. It does not even have a name. It is just a tireless traveler to unenlightened spots." I would like to end now with a somewhat different closing comment. Last week I took part in a dissertation for a so-called pseudo-degree of philosophy in fine and performing arts at the Center for Intellectual Art, connected to the Alma Löv Gallery in Värmland, Sweden. Has anybody been there? It was closed, it's open again. It's worth going to. It's close to Mårbacka, where Selma Lagerlöf had her residence. Okay, at this remarkable gallery there was this dissertation, and the thesis was on quantum art and interactual reality. Quantum art and interactual reality is really a crossover product. Presented by the Professor Emeritus in Theoretical Physics and Physical Resource Systems, Karl-Erik Eriksson, who served at Chalmers before he retired. He's now half-time chief in a village in Ghana, and is 79 years old. A main point in his thesis is that the situation in the world today makes it necessary to stress the common sooner than the differences between human cultures. We may have different perspectives sometimes, but the world is one, and so should culture be, is his idea. If we look at what happens today in Ukraine, Gaza, Iraq, Syria, we see the necessity of making this point and working for it to be fully acknowledged. One humanity, one world, one culture. Let's transgress our boundaries and serve in this program for our common world, even if we are just small butterflies. Thank you.
Thank you, Bengt Gustafsson. Just on the behalf of us who go on stage a lot, I'm an opera singer, and on the behalf of actors, we have a lot to learn from your rhetorics. Thank you.
Thank you.
Some questions.
You spoke earlier about the wondrous success of mathematics and science, and why that is so. I would like to question that premise. My background is in biomathematics, and we don't have the luxury of isolating systems as easily as physicists do. So it's not always just as good a fit. And there have been perspectives that question, even in domains such as physics, the wondrous fittedness, because one has to structure specific cases of these theories to fit and one has to even experimentally construct these conditions, so we have only a few points in which the theory and empirical evidence can fit, and we can find some kind of structure. So I was wondering what you think of this.
It's hard to give a general comment. I would like to say that it was not my intention to express the idea that everything can be written, it can be analyzed with mathematics or described with mathematics, not even in physics.
Yes.
I think we have a selection method. We select the simple systems and we forget about the complex ones because they are too difficult for us.
Yes.
And we don't have a proof that we can handle them ever with the present tools. However, what I would like to say that I am impressed to the extent it is possible.
Yes.
It wouldn't astonish me if it weren't possible at all to do anything in, say, elementary particle physics or cosmology with mathematics.
Yeah.
But in fact, it is indeed. And as I see it, if you want to make a conclusion from that in general terms, I think it's fair to say that for some reason I don't understand why, the universe is simpler or much simpler than we had any reason to believe.
Yeah.
And that is probably it's more woven in one piece than we had reasons to believe. And that's probably the kind of provisionary but a reasonable conclusion to draw.
So the very appearance of any structure in sense at all is the surprising aspect.
Yes.
Yes.
But what I want to stress, I think there are some important and meaningful questions to contemplate here for philosophy, and for science, and for sociology. By the way, also, why is mathematics so efficient? And there's also for those who are interested in aesthetics, there's an interesting aspect here. We don't have, as far as I can see, detailed or a careful analysis of the aesthetics of mathematics, aesthetics of science. What is beautiful science? I can give you a number of very beautiful science examples, but I don't know. I'm an amateur philosopher here, and so are scientists. I think somebody should really discuss these things from a philosophical
it would
perspective.
definitely be very interesting.
Yes. What is a beautiful experiment, and why is it beautiful?
Yes, or a beautiful equation.
Indeed.
Well, first of all, very peaking lecture. But I have to challenge you, Professor Gustafsson. I think you're a bit of a tease, because halfway through, or two-thirds of the way through, you said to us that you feel as though if you try and follow your ideas through about the formation of the universe while we're here, and that these turns out a bit like the Just So stories.
Yes.
And you've just said you're an amateur philosopher, so you must be coming to your own feelings of how is it here? Why is it so? And I think you've left us hanging that we didn't get that. Can you say in a few seconds or minutes, what is your feeling if it's not Just So stories?
Yeah. Being human, also being a scientist, means that you have to live with mixed feelings. I belong to the group of people, I have several colleagues. Martin Rees is one good example. He's a leading British cosmologist and astrophysicist. And he says the following thing, that this idea about our universe being special, which then with the scientific arguments implies that we have an enormous multitude of universes, and we happen to be born in, just as we are born on a planet with a reasonable temperature, we are born in a universe with reasonable laws of nature. Okay, this idea with the multitude is difficult to swallow because it gives the feeling that we make so much metaphysics in order to understand our small piece of physics. So we postulate such a huge invisible world in order to understand our part of it. So he said that he believes in this only on Monday mornings. And the rest of the week he doesn't know. And I'm afraid I could say Monday and Tuesday, so I could preach it today, but on Wednesday I would probably have said something else. Is this too bad.
Thank you so much for an unsurpassable painting about order and chaos. I liked very much two remarks of yours about about society and social order and living in society. You said that order in society is important, ordering society. But you also said that this is artificial, because what is order in time will looks like a disorder in other time. I liked very much this remark. And then I liked your last remark, your conclusion, a little bit puzzling one. Stress for mankind and for the world of people and culture, we should stress the common and not the different. This is to be discussed. I mean, the different is fantastic. Mankind looks like a huge painting because of differences here and there. One should penetrate the secret and mystery of those differences and enrich them and protect them. Thank you.
Thank you. If I may comment on that, I would like to show a picture which I usually show in the end of my talks, but forgot to show today. And that's this. It should be darker in the room, you would see it better, but it's Giorgione. This is around 1508 or so, Venetian, difficult person. He has left a number of paintings. This is in Vienna. And it's called The Three Philosophers, or The Three Wise Men, or things like that. If you look at the three guys, this is a person who has notes in his hands, and if you look closer, they are, lo and behold, astronomical or astrological annotations. So that's me, you know, talking to you guys. And this middle person, this type of picture which was often made showing wisdom, prudentia. Okay. The middle person is a man of power. On certain pictures he has even a sword to symbolize that. He stands and looks carefully at this fellow, a bit skeptical though. But the third person, a man or possibly a woman, equipped with some scientific tools. There is a ruler here, maybe a paper, maybe a compass. Looking into what? And if you look carefully at the painting here, you will see very brushy, very rough painting styles. While here, if you look at the borders here with very fine handicraft, it's so detailed. Okay?
Could you comment these three facts? First, there's no self-similarity in nature, only semi-self-similarity. Yes. Okay, you agree? Then second, if one proves that a model of a system is chaotic, it doesn't necessarily follow that the system self is chaotic. Do you agree?
Absolutely. This is quite interesting. The simplest way of describing a system in certain cases is certainly to say it's a chaotic system. While if you go in detail and study it, you may find structure in it which indicates it's not. It's not trivial to say, for sure, be sure about the system being chaotic, not even in theory.
My third claim is that actually everybody knows Mandelbrot fractal, but it's a fake, it's an artifact, because if you go from bottom up, it's just a jelly.
Yes.
Okay.
I agree. That's why I didn't show that. That was another fractal.
Thank you very much, Bengt Gustafsson.